last night. Any issues with the homework? Got a quiz on that today. Any problems there? Everybody's good with that? 4, yeah. So 4 on the answer key, you should have gotten the same answer. On the answer key, I had subbed in a different value for R because I converted my pressure to ATM, but you should have ended up with the same answer either way. So on the answer key, this value down here was different. It was like in the 700s, and I had this as, or no, it would have been, I think in the answer key I had this in like 0.74 or something. Because, let's see, 550 divided by 760. But you should end up with the same answer. So if I had this, instead I had 0.724, but I had a different R value, which was 0.0821. But the answer should have ended up being the same value. So if I take 0.425 times 62.4 times 310, did you convert your temp to Kelvin? And divide by 550, your answer should have been 14.9. And that would have been liters. Yes? Any other questions on that guy? Any other questions on the ideal gas law? Okay, well, then let's switch over to gas stoichiometry. So gas stoichiometry, we've done stoichiometry before, right? And when we were doing stoichiometry, I made you do those BCA tables, and I told you that you could only put moles in the holes. Do you remember me saying that? Only moles in the holes? Well, we can actually put in liters in the holes too if we're comparing gases. So they have to be gases. So for example, here, this is a gas, this is a gas, this is a gas. This is probably a liquid here. But we could, any of these things that are gases, we can convert liters to liters with them. So for example, if this one we had 15 liters of this, and we wanted to know how many liters of oxygen, we would just take the 15 up into the cloud. We're going to divide by 1. So our cloud is going to be 15, and then coming back down out of the cloud, that would give us 30 grams, or 30, not grams, 30 liters of oxygen, because these are gases. That's what that G is for. Okay. So that's what we're talking about. We can use those as mole ratio. Instead of mole ratios, we can use ratios for liters then too if we're comparing gases. All right. So to start with, if we are working at STP, the first thing is you have to have a balanced chemical equation. On your quiz tomorrow on these, I've already got your equations balanced for you. I have your formulas written out for you. So you should be okay with that. All right, here we're combusting 4 liters of propane. And they want to know how much oxygen. So can you tell from those ratios how many liters of oxygen you're going to make? 8, yeah, because 4 divided by 1 is 4. 4 times 2 is 8 liters of oxygen. Just ratios. Make sense? All right, now, as we move on, we need to talk about when we're not at STP. So, and when we need to get into grams and that sort of thing. So that means that we're going to be using our ideal gas law. All right. So the first one here we're looking at, we are going to take, we're synthesizing or making ammonia. All right. So I'm going to take some nitrogen, I'm going to take some hydrogen, and I'm going to make NH3. And then I need to balance my equation. So even and odd, I double the odd. So I'm going to double this, and then that's going to force me over here to write in a 3 for the hydrogen. So we are given 5 liters of nitrogen. We're trying to go into grams of ammonia. So I need to take my 5 liters of nitrogen here, and I need to figure out liters of this guy. So take this up into the cloud by dividing. 5 divided by 1 is 5. Then 5 times 2 is 10 liters. Okay? So now we know the liters of our ammonia. We can solve to figure out grams. So if I am using my PV equals nRT formula from yesterday, I am focused on getting this value isolated, and then I can turn that value into grams. So I want N by itself, so I'm going to divide both sides by RT. Then I'm going to plug in my values. My pressure is 3. My volume, I'm working on ammonia here. So I'm working on ammonia. I need the volume of the ammonia for this spot right here. It has to be the ammonia in there because that's what we're trying to solve for. Okay, so that's going to be 10 liters. Then I'm going to divide by R. I'm going to find my pressure in what units it's in. And then I'm going to convert that into, or I'm going to get my R value based on that because that's what drives your R value. So for ATM, that's 0.0821. And then my temperature is already in Kelvin, so I'm just going to put that down. Okay. So at that point, I get an N value of 1.23 moles. Moles of what? NH3. So that's what we were trying to find. All right. They didn't want to know moles. They wanted grams. So I'm going to take this. I'm going to take a nitrogen that's 14, and I'm going to add 3 hydrogens at 1 each to get 17. So 14 plus 3 is 17. Shoot, hold on. I put that in the wrong spot. That's why we write down our units first, and then we write down our numbers. All right, there we go. Now I got them in the right spot. My moles are going to cancel. That's going to leave me with grams. So that ends up being 20.8. That is grams of NH3. All right. one's balanced. I want to try to use one that's not balanced. Yeah, that won't be balanced. Yeah, that won't be balanced. Okay, good. I want this one. All right. I want to put a 2 here. I want to put a 2 here. All right. And we're looking at water vapor and methane. So good. I wanted something where I had different amounts here for coefficients because I want to make sure that you understand still your stoic. Okay. This guy, before we even get started, we're going to convert him to Kelvin. He needs to be 473. And I think we're good. All right. So I have 10.5 liters of methane gas. That means that my cloud is going to be 10.5. And that means that I have how many liters of water that I'm going to produce? 21. Yep. Okay. Then I want to know moles of water vapor. So I'm solving for N again. My pressure is 1. Which volume am I going to use? The 21 or the 10.5? The 21, because I'm trying to find out water. So that's the volume that I want to use there. Pressure's an ATM. And temperature is our 473. I ended up with 541. And that's going to be moles of what? Water. Yep. Water vapor. All right. Questions about any of the values, anything that I got for that problem, how I did it, anything that doesn't make sense? All right. Okay, so here we are starting for this guy with iron. Okay, iron is not a gas. So we can't try to figure this out and work back and forth with our ideal gas law on that guy. Because this is grams. We need to convert this guy into moles first. So I'm going to convert him into moles. How do I get him into moles? Divide by the molar mass, which I think is, hey hon, how you doing? Okay. We are working on some notes here. Okay, thank you. 55 point. Yeah, that's right. 55.5. 55.8. Good grief. 55.8. I'm going to divide that out. That's going to give me my moles of iron. So 52 divided by 55.8 is 0.932. So I'm going to have 0.932. I'm going to take this, I'm going to divide it by 4 to get it up into the cloud. So that's going to be 0.233. And then I'm going to take it and I'm going to multiply it by 2 in order to get it out of the cloud. So that's 0.466. Did they want? No, they didn't want that. Hold on. I need to divide it by, I need to multiply it by 3. That guy times 3. So we wanted the oxygen. Sorry. 0.699. Okay. So I didn't really need to figure this value out here. I needed this guy right here. All right. So we know our moles now. This is going to be our moles of oxygen. That's not what they wanted. They wanted the volume of oxygen. Now, since this is an STP, we can take that. We can solve this two different ways. I can solve it this way, where I take the moles of oxygen, and I know for every 1 mole, I have how many liters of gas? 22.4. Now, this only works when you're at STP. Okay, so there's a little shortcut that you can do for this one. So that gives us 15.7 liters of oxygen. The other way you could do this, and you should come up with the same answer, is you can solve for volume using your ideal gas law, where this is your mole amount. My temperature is 273, and my pressure would be 1 atm. So when you solve all of that, you should come out with the same value for your answer, or within a heartbeat away. Yes? So you could actually do this two different ways, since this is at STP. Now, if it's not at STP, you can't use this method here to solve for it. This is only when it's at STP that you can take that shortcut. Okay? So let's look at a couple other ones here where we can't take the shortcut. Find one. I should have one here. Come on. That one's all balanced up on us. I had one before. Thought. Maybe it's this one. Okay, let's get back to this one. Number 7, ammonium nitrate is a common ingredient. Could you find that one for me? Oh, no, that's at STP too. Darn it. Why can't I find anything that I want? Yikes. All right, well, we're going to take this guy. We're going to do him. We're going to... Are there some better ones? Yeah, let's do this one. I'm going to take this guy out of STP. What's your birthday? Yeah. So February 4. So we're going to be at 204 Kelvin and a pressure of, what's your birthday?
February 11th.
Not very inventive around here, but we'll go with it. Let's do that as kilopascal. All right. So, step 1, we are going to start with our balanced equation. So we've got potassium, we've got chlorine gas, and we're making potassium chloride. 2 and a 2. All right, yeah, that'll work out then. So, we're going to take this, and the first thing we need to do is we need to figure out moles. So I'm going to take this guy, I'm going to divide by the molar mass of potassium, which is 39.1, and that's going to give me my moles of potassium to put down here. All right, so remember, when you do these, you need at least 3 sig figs. Am I at 3 sig figs right now? No. Am I at 3 sig figs now? No. Am I now? Yes, I can stop. When you are doing these, at least 3 sig figs in this table at all times. Otherwise, you're not going to get good values. So I'm going to take that up. I'm going to divide it by 2. And I'm going to multiply it by 1. And that's going to give me my moles of Cl2. So then I can go 0.00261. That gives me my 3 sig figs. Do I need to bother with this guy? No, because I'm not using him for my problem, so I'm not going to keep going over here to write stuff out for him. I'm just going to stop where I'm at. All right, so this is going to be my mole amount for my problem. I am solving for liters, so in my ideal gas law, what variable is that? V. So I'm solving for V, so that means I'm going to have nRT over P, and I'm going to start plugging things in. So my mole amount here is going to be 0.00261. My pressure, I said, was in kilopascals, so I need to use the R value for kilopascals. And then I need to use the temperature in Kelvin. Barely got that one squeaked in there. And then I'm going to divide by my pressure, which we said was 211. All right, so I'm going to take this guy. I'm going to multiply by 8.314 times my temperature. And then I'm going to divide by my pressure. And I ended up with a volume of 0.02097. And that's going to be liters. If I wanted to convert that into milliliters, I would go 1, 2, 3. That would be 20.97 milliliters. What did I do? Yes. So my pressure is in kilopascals. So for my R value, that's driven off of what your pressure is given in. So if we go back up to the notes from yesterday, you will see that when pressure is given in kilopascals, our R value is 8.314. Good. And I'm letting you use one of these on your quiz today, and it has those R values on here for you. So you don't have to have them memorized. And I literally took this very diagram and just cut it down, made it a little bit more concise for your quiz. So. All right, are those making sense to you? Do you want me to do another one for you? Anybody want another one? All right, well, hopefully this video will work.